So in the previous lecture, we actually will talk about the transparency of the flip-flops. But I found a good example on the internet, so I prefer to share it with you to make you understand the concept of transparency. So, for example, here you have the we have two types of I'm sorry. The clock, if you see the clock here, we have 0, 0, and 1, 1. If you look at this clock and we have another input, the input here is 0, 1, and the output is always Q, Q is the previous state. So this means, this means, uh, this means the clock will keep the previous state irrespective of the input. Whatever the input, the previous state will be hold. The previous state will be hold. Okay? This is not transparent. This means this is not transparent. This part. This part is not transparent. Okay? Okay. What about this one? This one means we have an input 0, the output will follow the input. So the previous state or the previous state is going to be, or the current state will be always 0, irrespective of the previous state. There is no mention of the previous state. This means transparent. Transparent means that 0 appears in the input, appears at the output. It's like here, if you have a mirror here, the mirror, sorry, the mirror is not transparent, like a glass, like glass here. So 0, it will pass through the glass and appear at the output. 1 appear through the glass and appear at the output. So this means transparent or transparency. Transparency means whatever the input, it will appear at the output. Whatever the input, it will appear at the output. The opposite is the opposite. Sorry, the opposite is opaque. Opaque means the means there is no thing in there is no connection between the input and the output, and the output will depend on the previous state, on the previous state. So, for example, here 0 uh, with 0 input, we have a previous state uh, will be kept, and with 1 input, the previous state will be kept. Okay, this is the meaning of transparency. Transparency means whatever in the input will appear at the output, and I will, okay, let me, okay, move to, so today's lecture is talking about JK flip-flops. We will talk about JK flip-flops. The JK flip-flops, the symbol for it is like that one. We have two terminals or two input J and K. We have the clear, which is negative, and we have here the output. Okay, the flip-flop is just a modification version of the SR flip-flop. So it's just a SR flip-flop, and it has three different operations. It sets Q to 1, or resets Q to 0, or complement the output. Complement the output means if the input is 0, the output will be 1. If the input is 1, the output will be 0. So this is the JK flip-flop. The structure of the JK flip-flop is just an SR master-slave flip-flop with adding an AND gate here at the beginning of each input. So we have J with an input from the previous negative state, and K from the previous of positive state. Adding them together, we will go to S and R, and we have the master-slave fashion. As you know, this is going to be an edge, not edge triggered, sorry. This is level triggered flip-flop, level level trigger. And as I told you before about level triggered and edge triggered. Edge triggers the transition from 0 to 1, or the transition from 1 to 0. This is an edge trigger. But the level trigger means the flip-flop will be active on with whatever level you select, either level 1 or level 0. This is level triggered flip-flop. And this is the characteristic table of it. We have J and K. If we have an input 0 for J and input 0 for K, there is no change for the previous state. And the input 0 and 1 means reset. So J is resetting the entire flip-flop. And 1 0 means set. Set means put the output to be 1, or the next state to be 1. And if we have 1 and 1, this is going to give us a complement of the previous state. So if the previous state is 1, this is going to give us 0. If the previous state is 0, this is going to give us 1. So we have here 0 0, keep the previous state, and 1 1, flip the previous state. Flip or change the previous state. If it is 0, it comes to be 1. If it is 1, it comes to be 0. And here we have J. This is the master. This is the master input. So this means reset, and this means set. This is the characteristic equation, or the characteristic table of the, or the truth table of the flip-flop. So the J sets 1 and resets by 0, and complement the output, the previous state, and no change for the previous state. And these are the symbols for the master slave flip-flop. The SR flip-flop, we have trigger, this is an edge triggered, positive edge triggered flip-flop. This is not edge triggered, it is level triggered. Positive level triggered SR, and this is negative level triggered SR, and this is positive level triggered JK, and this is negative level triggered JK. These are the symbols, because some of the design may be, if you are asked to design, you can design just one like that, but if you want to design this from the internal structure of it, you have to expand your design. This means you have to get into the internal gates of the SR and implement it. But if you are implementing very complex systems, so you can use these building blocks for your system. And this means postponed output. Postponed output, we can hold it, means that we can hold it, means it is not transparent. Not transparent. This means this means the output is not transparent. So we can hold it. Hold it means if we want the previous state, we want to keep it, we can keep it irrespective of the input. This is the converted L-shaped letter here, means we can indicate the postpone output. The circle indicates a negative. So the control here, 0 will activate here, not 1, because we have a bubble here, means 0 will activate the gate, the flip-flop. Okay. Okay. This is an edge triggered flip-flop. This is the concept of edge triggered. This is the edge triggered flip-flop. Ignores the pulse while it is at constant level. Triggers only during the transition of the clock signal. So the activation signal is the transition from 0 to 1. This is positive edge triggered flip-flop. We have from low to high is positive edge triggered, and from high to low, this is negative edge triggered flip-flop. Okay. Let us investigate the GK flip-flop, the GK flip-flop characteristic table. If we want to describe the how we get, or how to make, how to say this, if we want to drive an equation, we want to drive an equation, how to drive this equation. We have the JK flip-flop as we have seen before. 0 0 will not change. 1 1 was going to complement. 0 is going to reset. 0 in J going to reset. 1 in J going to reset. Sorry, 1 in J going to sit, and 0 in J going to reset. Okay. Okay. This is the present state, and the Q of t plus 1 is the next state. This is the next state. Okay. Here we classify the flip-flops according to the response to the clock. This is response to positive level. This is positive level. This is positive edge response. Positive edge response. As you see, the arrow point is upward. Here, negative edge response, the arrow point is downward. This is straightforward, no need to expand it further. We will move to another type of flip-flop, is D flip-flop. As we have seen, JK flip-flop, don't forget the characteristic table of the JK flip-flop. If we have 0 0 means there is no change in the previous state, 1 0 means set, 0 1 means reset, and 1 1 means flip the previous state. This is the D flip-flop, which is another one, and also edge triggered D flip-flop. We have the master slave style. Here the SR and SR latch, and this is D latch, and this is the connection, this is the control. The control is negated to be a master slave structure. We have different symbols for the D flip-flop. We will see now how it is working, but we need to see the symbols for the D flip-flop. We have the positive edge triggered D flip-flop, and this is negative edge triggered D flip-flop. We have here this is the clock. This is the clock, and this is the negative clock. As you see, we have a bubble here. If you notice, this is a bubble, means it is this triggered at the negative, if you see. And the triangle is called dynamic indicator, means it's going to be changed whenever an edge trigger like this is happening. Is not control like, okay, the triangle is misleading a little bit. The triangle here means what? Means if you remove this triangle, means the control is when it is 0, it deactivate the entire set. When it is 1, it activates the entire set. But here means it is a continuous. So 0 and 1 is going to be changed by time. This is the meaning of this triangle. This means it is going to change by time. So we have many positive edge triggers here. We have many positive edges, and whenever a positive edge is happening, the D flip-flop will be activated. And this is the characteristic table of the D flip-flop. Is more simpler than JK flip-flop. It is we have D. This is the input and the Q of t plus 1. So it is 0 for set, and 1 for 0 for reset, and 1 for set. And the characteristic equation is, this is the D flip-flop, sorry, this is the D flip-flop, sorry, this is the D latch, yes, not the entire D flip-flop. This is not D flip-flop, just we describe the characteristic table. Oh, the word the characteristic is very hard to pronounce, and administrator like that. Okay, anyway, the D flip-flop The D flip-flop is the entire set here. We have D latch and SR latch. They are constituting the entire D flip-flop. But here we talk about the D latch. Okay, this is the D latch. Okay, so the characteristic table equation of the D latch is Q of T plus 1 is equal to D of T. Okay, we have other types of flip-flop that can be, sorry, I think we have here, this is the D flip-flop, not the D latch. D latch is holding the data, but the D flip-flop is, okay. Oh, yes. The difference is, what is the difference between D latch and D flip-flop? Yes, yes, I understand now the difference. The D flip-flop here is old style, so we can clear by using the clock. But here, the flip-flop means that it is changing every edge. This is the difference between D latch and D flip-flop. The D flip-flop means we have a clock that is changing by time, and at each edge trigger, so it is going to change its state according to the input. So this is the D flip-flop. This is positive edge trigger D flip-flop, and this is negative edge trigger D flip-flop. Yes, and this is the characteristic table of the D flip-flop. This is actually the D flip-flop. We need it in the registers when we design RAM and registers for the processor. And we have also two types of commonly used flip-flops, the edge trigger JK flip-flop and the T flip-flop. The characteristic tables. Here we have a characteristic table for the edge trigger the JK flip-flop. The characteristic equation is Q of T plus 1 equal to J of T Q dash of T plus K dash of T multiplied by Q of T. How this equation is derived, and this is we're going to explain it here. We have the input 1 1 means complement, 1 1 0 0, sorry, means no change, and the characteristic equation is J Q dash K dash Q, J Q dash K dash Q. How to get this equation? Just expand this truth table to more comprehensive one. So we have J in one entry, K in another entry, and Q, which is the previous state, and the clock value, and the Q plus, which is the, you can say, the next state. This is the current state, and this is the next state. So if we have input 0 0 and the current state is 0, the next state is going to be 0. If we have 0 0 and we have 1, there is no change. It means this one is going to be moved to 1. For 0 1, this is going to always have 0, because this is reset. The next state always will be 0. And for the set, we will have the output will be always 1, because this is the set state, which is 1 0. The last one is flipping. Flipping means 0 will be flipped to 1, 1 is going to be flipped to 0. Now I want to write an equation for the output. I want to write an equation for the output. Okay, just make the table, this Karnaugh map, using the Q and JK. These are the inputs. We have J and K and Q, which is the current state, and we drive the ones for the next state. I want to know the next state, given the input and the current state. So this is the function. So I take the one here and put it in the corresponding table, place or location, and we take the one here, put it here, one here, put it here. Okay, let's see it. If we have Q, J, K, these are the inputs for the next state. We have the previous state and the input J, K. And here for 1, we have 0, 0, 1, 0, 0, 1. So this is the first one. And the second one here is 1, 0, 0, which is 1, 0, 0. This is the second one. This one, 1, 0, 1, 1, 0, 1. This is the one. This is the corresponding one here. The last one here, we want to put it in the table. We see it is 1, 1, 0. So 1, 1, and 0, which is this location. So we get the Q plus and put it in the Karnaugh map. And as we have seen before, we collect these ones together, and we collect the two ones at the edges, and then we can derive the characteristic equation. Q of t plus 1, which is the next state, is equal to J multiplied by Q dash plus K dash multiplied by Q. Okay, this is the characteristic equation for the JK flip-flop, and the way how to drive it using the truth table. If you want to drive if any of the JK flip-flop characteristic equation, you should be able to define the inputs, the previous state, then you can derive the next state. Sorry, this is not the previous state, the current state. So the inputs and the current state, and you can drive the next state. Okay, and this is the way how to drive the JK characteristic equation. What about the T flip-flop? Actually, all these types of flip-flop, D flip-flop, T flip-flop, and JK flip-flop, all we are going to use them to make shift registers and counters in the next lectures, inshallah. So this is the T flip-flop. The T flip-flop is an abbreviation, is the same as JK flip-flop, but we have only two entries. The first entry is 0, which is the T here. Whenever it is 0, so we keep the previous state. Whenever T is 1, we complement the previous state. So if we have encountered 0 here, this state is going to be no change. If it is 1, it is going to be remained 1. If it is 0, it's going to be 0. But here, if T is changed to 1, this is going to flip the previous state. So the previous state is 1, is going to be 0. If it's 0, is going to be 1. This is the characteristic equation of the T flip-flop. The same as JK flip-flop, but just with two entries. Okay, so we have the characteristic equation as we have derived for the JK flip-flop. Here, Q equal TQ dash plus T dash Q. This is very simple. Q equal TQ dash and T dash Q. Of course, you can do that on your own. You can derive a comprehensive truth table from this small table. Just put the input, which is T, okay, and the previous state, which is Q, and then derive the corresponding truth table, and then use the Karnaugh map or direct mapping to get this characteristic equation. How to get the T flip-flop from the JK flip-flop? We can do that just by using compacting if you see here we have 0, 0, so we have Q of T. If we have 1, 1, we have Q dash of T. This is the two entries here, and this is these two entries are not existing. But how to do that? We can do it simply by connecting the input. We have JK flip-flop. We can connect the JK together. We connect them together, and this is the T, and we have output Q, which is the current state, and Q dash, which is the complement of the current state. So the T flip-flop is obtained by combining or just connecting the two inputs of the JK flip-flop together. We tied them together. So we have here the characteristic equation of the JK flip-flop. We tie them together to get the T flip-flop operation. Okay, About the summary characteristic equation, the D flip-flop can be expressed at D. Just the characteristic equation for the D is Q of T plus 1 is equal D. For the JK flip-flop, Q equal JQ dash plus K dash Q. For the T flip-flop, Q equal TQ dash plus T dash Q. The characteristic tables are used to derive the characteristic equation and analyze sequential sets. What about the set and reset inputs? What about the set and reset inputs? The set and reset inputs, they are independent of the clock. They are active low. For example, this is the set and this is the reset here. And you see we have the D flip-flop. It contains set and reset. This is just this slide is meant to do what? Is to tell you that the set and reset is a master reset, like a hardware reset. This is a hardware reset. We want to reset the data, so this is just a hardware reset. As you do in the computer, you post you sorry you put sorry oh fasting okay the set in the computer. If you press the set button, the set button or the reset button is going to close the computer and reset it again. This is the same concept here. We have the set and reset. This is active low, means at 0 is going to set the D flip-flop. Here at 0 is going to reset the flip-flop. So if you see the set and reset here, if you see this is the set here is active low, means this is going to activate the flip-flop because the output current value is 1. Here input 0 because it is active low. Okay. And here the reset also means if the reset is 0 means it is active, means it's going to activate to reset the to make it 0 or to stop it. The timing. Actually, this is the last lecture, the last slide for today. It is a time about it's talking about timing. It's talking about the timing. We have the edges here. We have two different types of timing. The TS, which is the setup time. We call it setup time. It's just before the edge is happening. And the hold time. This is after the edge is happening or the edge is triggered. This is the hold. We call it the hold time. The time input must be stable after clock edge. Okay. Okay. If you have any questions for today's lecture, you have any question? I have finished the lecture. If you